Good morning, ladies and gentlemen. For our next thermodynamics lesson, we're going to talk more about pressure volume graphs and how the formulas we've learned so far apply to pressure volume graphs. This is one of the more common types of questions on the AP, so let's just assign some numbers and we'll play around and see how we use the formulas. So let's say for this pressure over here that the pressure is 5 times 10 to the 5th pascals, or newtons per meter squared. We could say that the initial volume, let's pick an easy number, let's say it's 1 meter cubed, and expands up to 5 meters cubed. There are 300 moles of nitrogen in this scenario. And what can we ultimately solve for? Well, if I want to solve for the initial temperature at that location, knowing the initial volume, knowing the pressure, knowing the number of moles, it's very straightforward to end up using PV equals to nRT. Because with our given information, temperature simply equals to the pressure times the volume divided by number of moles times the universal gas constant. So if I plug this in, and it ends up being 5 times 10 to the 5th pascals times 1 meter cubed divided by 300 moles times 8.31 joules per mole Kelvin. If I plug that all in, I end up with 200.56 Kelvin. Okay, so that's just a basic way of solving for the temperature, knowing the number of moles at any point on a PV graph. But what if I want to know the temperature now at the second location? Well, there are a couple different ways we could go about solving the temperature at the second location. We could redo PV equals nRT all over again and plug in all the numbers and get an answer. But there's an easier way to do it. You see, rather than using the ideal gas law again, we can use the combined gas law, which means P1V1 over T1 equals P2V2 over T2. And we can use this to calculate what the new temperature is automatically. You see, we know that from the initial location to the second location, pressure does not change. So technically, that can be taken out of the equation. So you're really just left with V1 over T1 equals to V2 over T2. And remember, in this type of multiplier question, all the multipliers need to cancel out. So as it went from V1 to V2, the volume increased by 5 times. So it's 5 V2. So if the volume increased by 5 times, that means the temperature must increase by 5 times as well. So if the initial temperature was 200.56, then the new temperature will end up being 200.56 times 5, or 1002.8 Kelvin. Okay, so understand you can either use the ideal gas law, PV equals nRT, or the combined gas law. If you do not have number of moles, then you can't use the ideal gas law, and the combined gas law is probably the way to go. Now, after we solve for the temperature at each location, I'm just going to round it right now to 200 and 1,000. There's one other piece of information I can solve for, and that's what was the actual change in the internal energy of the gas. Now, when I say internal energy, that's of course delta U. We can't quite use delta U equals Q plus W yet. We can solve for the work involved, but we don't know heat. So rather than using delta U equals to Q plus W, we could use delta U equals to 3/2 NR delta T to solve for the change in internal energy based on the change in temperature. So that would equal to 3/2 times 300 moles times 8.31 joules per mole Kelvin times 800 Kelvin, and you would end up with a very large number. Delta U in this case is equal to 2.99 times 10 to the 6th joules, which may or may not be entirely realistic in terms of actual real-world numbers, but you can see it's a very straightforward way to solve for internal energy. Once you know the two temperatures, you can always solve for delta U. Now, the thing is, what else can we solve for on this graph? We can also solve for the work done. Not with any formula, though, straightforward-wise, but rather by looking at the graph itself. You see, in this case over here, I should remember that the work is equal to the area underneath the graph line. Work, in this case, we could use P delta V because it is a constant pressure, but I'm simply going to write out it's going to be negative 5 times 10 to the 5th pascals, which is the height of the rectangle, times the base, which is 4 meters cubed, which ends up equaling to negative 2 times 10 to the 6th joules. Remember, it's negative work simply because the volume is expanding. But we now have the work. We now know the delta U. What could we solve for next? Well, if we know delta U, we know work, we could solve for Q. Delta U is equal to Q plus W. Q would simply equal to delta U minus W. Now, this is where you have to be slightly careful because of your negative signs. Okay, so it would equal to 2.99 times 10 to the 6th, which is really 3 times 10 to the 6th, minus negative 2 times 10 to the 6th. So you end up with 4.99 times 10 to the 6th joules would be the amount of heat that was added to the system. Okay, so at its most basic level, a PV graph seems very simplistic, but there's a ton of information that can be solved for from one simple line. We solve for the temperature at the beginning and the end of the line. We solve for the change in internal energy. We solve for the work. And then we were able to solve for the heat that was added or removed from the gas. Okay. Now let's take a look at some special situations for thermodynamics. And during these processes, you have certain variables that are held constant. Our first example is adiabatic. Adiabatic simply means that there is no heat transfer. So Q equals 0. Similar to, if you were to think about it, like a thermos. Whenever you put hot liquid inside a thermos, it stays hot because the heat inside is unable to escape out. Or just like if you put an ice-cold beverage in a thermos, it stays cold because the heat from the outer surroundings is unable to come in. So the fact is, whenever you have an adiabatic situation, there is no heat transfer whatsoever. Now the thing is, because there's no heat transfer, and knowing the formula delta U equals to Q plus W, that means delta U is equal to W. The change in internal energy is equal to the work that you put in. What does that really mean? Well, let's take a quick look at this example over here then. Okay. Right now I have an adiabatic situation set up, and the piston is closing in. It's doing positive work on the scenario. Notice what's happening to the temperature as we're doing positive work on the scenario. The more work you put in, the higher the temperature is, meaning all the energy stays inside and the molecules are literally moving faster and faster than before. So with an adiabatic situation, there's no heat loss out of the system. All the energy you put in stays in. And vice versa, if we were to actually move this piston back out, as the gas uses up its own energy to do work to expand, it'll cool off because it's losing energy. Delta U is equal to Q plus W, okay? So when you say a statement like that, think about delta U as a temperature, meaning that if you're doing work, the temperature goes up as well, okay? The temperature increases. If you were to graph what an adiabatic graph looks like, it would look like this. Whether if it's being compressed, then the graph line is going to go in one way, upward, because as the volume is decreasing, the pressure is increasing, okay? And in this case, Q would equal to 0, and you would have positive work, and therefore you have positive delta U, or positive increase in temperature, or vice versa. If you have the same graph line and going the opposite direction, that's when the gas uses up its own energy to expand outwards. So in this case, the volume is increasing, the pressure is decreasing. Q is still equal to 0, but we have a negative work and a negative delta U, therefore. Okay? So that's what adiabatic means. It's basically a thermos. You're completely isolated and insulated thermally. The next situation we're going to look at is isothermal. Now, isothermal, you can kind of guess, has something to do with temperature based on the word therm, and iso, of course, means isolate. An isothermal graph means that there is no change in temperature whatsoever. Now, the thing is, because there's no change in temperature, that means that there's no change in the internal energy of the gas itself either. When there's no change in internal energy of the gas molecules are still moving at the same speed, same average speed as before. And if we look at the formula delta U equals to Q plus W, and delta U crosses out, that means that any work you put in automatically gets lost as heat. Let's take a look at our situation again and see what that really means. Okay. So now I have this set to be an isothermal. Notice as soon as I click that isothermal button, we note that the change in internal energy, delta U, is automatically going to be 0, and that the work is equal to negative Q. So what does that mean? Take a look. Now, in this case over here, as the piston is compressing the gas, notice the speed of the gas on average is not changing. It's exactly the same as before. The same temperature, the same internal energy, which means that as it's being compressed, energy is being lost as heat. So when you're doing positive work on a situation, compressing the gas, the energy that's put in escapes, and the gas stays at the exact same temperature. Or vice versa, if I were to put this situation into reverse, unfortunately this demonstration does not do that, but if I were to put a candle underneath the situation, and I would be adding in heat. Now in this case, if under an isothermal situation, if I'm adding in heat and the temperature is still not changing, where does that energy go? Well, any energy I would be putting in would be pushing the piston back out. All the energy would be used up immediately by the gas to increase its volume. So whenever I have a positive Q, I have negative work. When I have a positive work, the energy gets lost as negative Q. So that's what isothermal means. Okay. Now, if I were to graph an isothermal graph, it will look very similar to what I just did before with the adiabatic. It will look like this. I'll talk to you in a minute about how to distinguish between the two, but for a moment, just bear with me, okay? In this case, with the isothermal graph, that means the temperature at location 1 is equal to temperature at location 2. If I set this up as P1 V1 over T1 equals to P2 V2 over T2, I would know that automatically T1 and T2 cross out. So as my volume is increasing, my pressure decreases inversely proportionally. Okay? That's different than when we were with the adiabatic. With the adiabatic system, we could not use the combined gas law as neatly because the temperature did not cancel out. But whenever you have an isothermal situation, you can automatically cross out the temperature. So in this case, if the volume, let's say, had tripled, that means the pressure would have to be 1/3 the amount of before. Okay? And in this case, we're assuming, of course, that it would be expanding outward, and you would have negative work being done. Or vice versa. If you were to have positive work done, if you compare the pressure and volume at location 1 and location 2, in this case, volume would be decreasing, pressure would be increasing. So let's say the volume, we have 1/5 the volume, so we do P and V. If we had 1/5 the volume from before, that means the pressure has to directly increase by 5 times. Okay? And that's Boyles Law. Okay. Our next word that we're going to define is isobaric. If you think about what a barometer does, a barometer measures pressure, isobaric simply means constant pressure. There's nothing that really crosses out in this situation, but understand that it's when you have a constant pressure, whether you have a negative work or you have a positive work. And because it is constant, you are allowed to use work is equal to negative P delta V as the formula. So isobaric simply means it's going to be expanding or contracting at a constant pressure. But note, because it is a constant pressure, just like we did in the example before, if I were to do P1 V1 over T1 equals to P2 V2 over T2, the pressure crosses out. That means that volume and temperature are directly related to each other. If you were to increase the volume by 3 times the volume, automatically the temperature would have to triple as well to cancel out that multiplier. Okay? So always keep in mind, and this is simply just another one of the gas laws, assuming that pressure is held constant. Isochoric, we've already done isochoric, you just don't realize it. We've spoken about constant temperature, we've spoken about constant pressure. Isochoric means constant volume, meaning either increasing pressure like that or decreasing pressure like that, but the volume stays exactly the same. And of course, because there's no delta V, therefore, work is equal to 0. So when I do delta U equals to Q plus W, this idea probably makes the most sense to you. Delta U is equal to Q. That means if I took my gas and held it inside a container of some sort, and the gas molecules are bouncing around, if I put a candle underneath and I started heating it up, but without letting the box change shape, then the fact is these molecules will start getting faster and faster as they're wandering or as they're bouncing around. Any increase in heat added automatically increases the temperature of the gas itself. It would increase the pressure. In fact, if you were to hold the candle under the box too long, eventually there'd be so much buildup of pressure inside that container that the container would actually have a chance of exploding outwards. Which is why whenever you have pressurized contents inside a spray can, like a spray paint, they always tell you keep it away from flame. Because if you put the spray paint near flame and it heats up the gas inside even more, that's increasing the pressure without changing the volume. It's an isochoric situation. You increase the pressure, you increase the temperature, eventually the spray can will eventually explode. Okay? So there's no work in either situation over here, but do keep in mind that we can still use PV over T equals to PV over T. Volume stays the same, so it crosses out, but pressure and temperature are now directly related to each other. If I triple the pressure, I automatically triple the temperature. Okay? So this is, again, the combined gas law here, which works out very neatly in this isochoric situation. The last scenario we're going to talk about is something called a cyclic reaction, and it's probably what we're going to see the most often. A cyclic reaction simply means that the gas returns to its initial state. Same initial pressure, same initial volume, same initial temperature. Okay? But because it is the same initial temperature, that means that delta T is equal to 0, which of course then means that delta U is equal to 0, which we've seen before with the isothermal situation. So it's similar how it works out math-wise, though it's a different type of situation. And in this case, again, any work done would therefore equal to negative Q. So if I were to start with my location over here, that means using a process of heating and cooling, I would expand the gas and cool off the gas until it went all the way around back to its initial location and back to its initial temperature. But this example over here with the weird oblong shape is a little bit counterintuitive to understand. Rather, let's take a quick look at this example below, which has a box. We're not going to, well, we can actually solve this one as well at the same time. Our initial location is at point A. It gets heated isochorically, so it goes to B, isobarically to C, then cooled off isochorically, then cooled off isobarically. So we have a complete cyclic reaction. Now, understand, if I were to separate this out into which lines are actually doing work, however, okay, AB and CD I know are isochoric, so there's no work done whatsoever. However, BC has a negative work, and all the area underneath BC would be a negative work value. My other line that also has work is from D back to A. And over here I have a positive work. And everything underneath D to A is positive. You can see that in this portion over here, the positive work and the negative work cancel each other out. And because they cancel each other out, that means for any cyclic reaction, okay, for any cyclic reaction, the work is equal to the area inside the shape. If it's an easy shape, then that's obviously how you calculate work. If it's a weird oblong shape, there'll be some other method to calculate it. Overall, because our negative work is greater than our positive work, it's going to be a negative work done inside. So if I want to solve for the net work done by the gas per cycle in terms of PO and VO, that means I just have to solve for the shape of the rectangle. The work is equal to, so the height over here is 2 PO. The width is 2 VO. So total work done would be 4 PO VO, which is of course negative because the B to C is a negative work being done as the volume increases. So this is the quick and easy answer to part A. But the thing is, how much heat was added to the system per cycle? Well, now that I know my work, and the key word here, of course, is cycle, because during a cycle, delta T is equal to 0 when it goes back to its original position, which therefore means that delta U is equal to 0. So when I do delta U equals to Q plus W, delta U crosses out. Q is simply equal to negative work. So in this case, would equal to positive 4 PO VO. And there's my answer for part B for the cyclic question. So whenever I have work being done, the exact opposite is happening with heat. Okay? So that is a cyclic reaction. So now if we were to just to quickly summarize all of the different processes that we've learned, adiabatic means that Q is equal to 0. We know that during isothermal, temperature stays constant, so delta T is equal to 0. Isobaric means that there's no change in pressure, and isochoric means that there's no change in volume. With cyclic, there's also going to be no change in temperature as well because you're returning to the original point. With delta U, because delta Q is equal to 0, delta U is simply equal to W and vice versa. And with delta T equals 0, then delta U automatically equals 0 as well, because with no change in temperature, there's no change in internal energy. So work would automatically equal to negative Q. Isobaric, delta U is just going to be the same basic form because nothing cancels out. Or we could have used also 3/2 and our delta T depending on the situation. And work would simply equal to P, negative P delta V. Isochoric, because there's no change in volume, then therefore work would equal to 0. And delta U would simply equal to Q. Okay, so that's just a quick summary of the different processes. I had mentioned before, how do you distinguish between an isothermal line and an adiabatic line? Well, in this case over here, when we have an isothermal versus adiabatic, the adiabatic will always have less work done. As you can see, it's lower than the isothermal line. But the reason it ends up being lower is simply because when you have an isothermal line over here, as the pressure is decreasing and the volume is increasing, Q remains constant. And normally you would lose heat, perhaps, but with the isothermal, that means there's actually an outside source of Q that's heating up the gas and causing it to expand. So it ends up at a higher temperature than the adiabatic line would. Okay? So that's the main difference. Okay. So let's do another practice question together. An ideal gas is slowly compressed at a constant pressure of 2 atm from 10 liters to 2 liters. So 10 liters to 2 liters. In this process, some heat flows out and the temperature drops. Heat is then added to the gas, holding the volume constant, and it rises until it reaches its original value, which we don't know exactly what it is. But this is what the graph looks like. We have an isobaric line and then an isochoric line. So when they ask us to calculate the total work done by the gas, well, the total work would equal to this area underneath the graph line, which would be positive work because the volume is decreasing. So the work would equal to the base times the height. So the base is 8 liters, which is 8 times 10 to the negative third meters cubed, times the height of 2 atm, which is 2 times 10 to the fifth pascals. You get a total work of 1,600 joules. What is the overall temperature change? Well, since the initial temperature and the final temperature are exactly the same, that means delta T is equal to 0, which of course therefore means that delta U is equal to 0 as well. So we're looking for how much total heat flows into the gas. That would simply be delta U equals to Q plus W. And with delta U equals to Q plus W, Q is simply equal to negative W, so in this case will equal to negative 1,600 joules. Okay, so that's a very straightforward question. Okay. A gas is expanded from a volume of 1 liter to 3 liters at a constant pressure of 3 atm. So 1 liter to 3 liters at constant pressure is then compressed until it reaches 2 atm, and then it's cooled until it reaches 2 atm, and then it's compressed back to 1 atm, and then it's heated until it goes back to its original state. So in this case, we can see that it is a cyclic reaction. And if we're looking for the net work done during the complete cycle, that would simply equal to the area inside. Now, because there's more negative work than there is positive work, our overall answer is going to be a negative answer. So our work is equal to, the height is 1 atm, 1 times 10 to the 5th pascals, times a base of 2 liters, or 2 times 10 to the negative third meters cubed, so work in this case will equal to negative 200 joules. Okay. But that's work for the entire cycle. That answers part E. I didn't solve for the individual work, but you can see that overall we can solve for the net work done. However, I want to add an additional part to this question. My question is now, which point has the highest temperature and which point has the lowest temperature? So overall, let's say that there are a total of 100 moles of gas. and I want to find what is the temperature at that bottom left corner. Okay, so the temperature at the bottom left corner will simply be solved for using PV equals to nRT. Temperature would equal to PV over nR, so that would equal to 2 times 10 to the 5th pascals times 1 times 10 to the negative 3rd meters cubed divided by 100 moles divided by 8.31 joules per mole Kelvin, which gives me a final answer of, give me 1 minute, 0.24 Kelvin. Now my numbers are not the best that I've made up, but it's okay. Right now we know the temperature is 0.24 Kelvin. Now using the combined gas law, we should be able to figure out what's happening to the temperature at each location. Well, overall, if you were to solve for the temperature at this location, we know that the volume has tripled. The volume has tripled. Well, that's PV over T equals to PV over T. The volume has tripled, but the pressure stays the same. That means the temperature must have tripled as well. So that means that the temperature at the second location would be 3 times 0.24, which is 0.72 Kelvin. Okay, so that's a nice, easy ratio for us to figure out. Now, if we're talking about what's the temperature at the top right corner, let's erase some of the work over here. Okay. Now, in this example over here, I know that the original volume was 1, the new volume is 3. The original pressure was 2, the new pressure is 3. I'm going to do PV over T equals to PV over T. Okay? You have to say to yourself, by what factor has these different values changed by? When you compare the very beginning to the very end. So, as I said before, the volume has tripled. The pressure has increased by 1.5. So that means if I want to cancel out all those multipliers, the temperature must also change by something that will cancel it out. So the temperature must have increased by 4.5 times. So the original temperature at T1 was equal to 0.24 Kelvin. That means my new temperature at that third location would be 1.08 Kelvin. Okay. Notice, and this is something you should absolutely keep track of. The highest temperature is always in the top right corner. Okay? That's always the highest temperature. The bottom left point, as you guys can see, will always be the lowest temperature over here. Okay? So top right is always the highest temperature, bottom left is always the lowest temperature.